Welcome to this webinar provided by Ultra Forensic Technology. My name is Michel Paradis, Senior Product Manager, and I will be your host. In previous webinars, we introduced the quantum 3D microscope, as well as the scientific foundation of its quantitative analysis component based on 3D measurements. In this webinar, we compare the effectiveness of the quantum 3D microscope relative to using a conventional comparison microscope by working a case scenario involving bullets and firearms. For those of you who may not be familiar with the GoToWebinar platform, here are a few tips. You can click the orange arrow to toggle the control panel on and off so that it does not hide parts of the presentation. I recommend clicking the full screen button to maximize the viewing area of the presentation. This will be especially helpful to better see images and detailed information. If you have questions, please type them in the questions area of the control panel. These will be sent to me, the host, and there will be time at the end of the presentation to answer questions. We expect this webinar to last approximately 1 hour. You will hear from 3 presenters. This study has been coordinated by Andy Boyle, and it involved the participation of 2 firearm examiners, Paul Murphy and Ron Nichols, who will explain their experiences and results. But first, allow me to introduce them. Andy Boyle has held multiple positions at Ultra Forensic Technology since 1994, including IBIS instructor and firearm subject matter expertise for the research team. In the last 9 years, one of Andy's roles has been to act as the liaison for the Interpol Ballistic Information Network. Working in collaboration with Interpol, Andy has traveled the world promoting the benefits of IBIS and the Interpol network to forensic firearm experts and government officials. Andy currently works in the marketing department and is responsible for trials and demonstrations of IBIS products in the quantum 3D microscope. It is Andy who has coordinated the study that is presented in this webinar. Next, Paul Murphy is currently the Senior Firearms Technical Advisor and Subject Matter Expert for Ultra Forensic Technology, a position he has held since 2005. Paul has been a forensic firearm examiner since 1984 and served in the South African Police for 22 years, including 15 years at their Forensic Science Laboratory, where he worked more than 6,000 firearm and toolmark-related cases. Before resigning in 1999, Paul established a Forensic Science Laboratory in Port Elizabeth and served as its commanding officer. Paul then moved to the United States and worked as a senior forensic scientist for the Virginia DFS until 2005, where he completed more than 2,000 cases. Paul has been an AFTI member since 1987 and a distinguished member of AFTI since 2000. Finally, Ron Nichols is the president of Nichols Forensic Science Consulting. He has been a forensic scientist since 1984 and a fully trained firearm and toolmark examiner since 1991, when he started with the Oakland Police Department in California and went on to work with the ATF. Since his retirement from the ATF, Ron has served as a private consultant and has established a training academy offering training for firearm and toolmark examiners. Ron is a distinguished member of AFTI and a fellow of the American Academy of Forensic Sciences. Ron is widely published, especially on the scientific foundations of firearm and toolmark identification. In addition to his book on that topic, he also contributes through training, lectures, and workshops. His goal has been to educate examiners in the scientific foundations of the discipline and provide training on in how to better articulate those foundations. I will now let Andy introduce the study. Andy?
Thank you, Michelle. So for today's presentation, I'll be going over the study overview as well as a bit of a review of the quantum product. And then we'll pass it along to Ron and later Paul, who will go through their examiner experiences going through the study itself. And we'll close with a discussion and question and answer session. So quantum 3D microscope is a workstation that allows you to do 3D data capture. So your items can go into the workstation here and get imaged, and then you are able to work with them in high resolution 3D here and perform comparisons. Everything is stored locally on the computer at the workstation itself. And the point of quantum is to allow experts to use all the experience they've developed as firearms examiners and apply that to doing 3D comparisons on screen of items such as bullets or even the outside body of cartridge cases for chamber marks, ejection port marks, areas such as that. It allows them to do that sort of work. All the experience they've developed over the years on the comparison microscope is immediately applicable to their work experience using the quantum software. In addition to that, you have the benefit of running quantitative analysis on bullet items that are being compared. And that will evaluate the similarity and establish a false match rate between the compared items. And because quantum is effectively a 3D microscope, it is calibrated using ISO 17025 certified targets. And so when you do run the quantitative analysis, you receive 2 scores that are charted out on what we call the Rebel graph, the RBL graph, named for the 3 scientists that developed it, Roberge, Beauchamp, Lévesque. And so the 2 scores are the pattern matching score, which is assigned, and that extends out horizontally. And then you also have the line counting score, which extends vertically. And depending on what those 2 scores are, your item comparison will be charted out on that Rebel graph with its ranking. And that is the false match rate, which is calculated on the combination of those 2 scores. And so here, if we just summarize what we see, there's a comparison right now between unknown 6 and unknown 8, the 2 items in question, and the pattern matching score is 0.62. And so across this one horizontally, 0.62, that's as far horizontally as it goes, and vertically 0.59, so just below 0.6 here. That charts out where it ranks within the Rebel graph. And that establishes what the false match rate is. You see a series of numbers here, 6, 8, 10, 12, 14, and beyond. Those are indicators that give you a sense of the positioning. And this one here is just below the 12 with an FMR value of 11.53. And so when we talk about the FMR, the false match rate for a given similarity score represents the probability that 2 bullets that were not fired from the same firearm would generate a higher similarity score. So that is what that is representing, that numerical value. And that numerical value is applied to a formula of 1 over 10 to the power of that false match rate value, 11.53 in this case. And that establishes an index of 1 over 300 billion in this particular example. There is also diagonally across the graph here what we call the separation line. And if you look at that numerical sequencing again here from 12 to 10 to 8 to 6, this would be where 4 is. So false match rate value of 4 is where that separation line appears. And it's important to realize this is not a pass-fail line or not a non-match below and it is a match above. That is not what that is telling you. The separation line is simply delegating where visual similarities between the items compared are going to become apparent. But it's up to you as the firearms expert to make your conclusion as to whether or not this is a match or not. And so you will find at times a match that is below that separation line. You might call a match on something positioned down here. You may well call a non-match on something that is positioned above that separation line. That is totally fine. But that separation line is basically indicating that similarities are becoming visible, and your expertise is determining, well, yes, they look similar, however, this is not a match because there's far too much subclass involved, or I do see a match, even though it's below the separation line. A match down in this area would likely have a lot of smoothness on the land impression surfaces, whereas the actual matching stria is a very small portion of the overall surface of one or both land impressions. There's more to the science of this, of course. This is just a review right now. However, this is our third webinar on quantum at this stage. The first two webinars delve far more deeply into the mathematical formulas, the background of the Rebel graph itself. If you have not seen those or would like to do a review of those, you can go to our webpage, ultra-forensictechnology.com, and go to the quantum product page, and you can find both of those previous webinars are available to watch from that page. You also have access to go to the question and answer page as well. The frequently asked questions there, the FAQ page has a lot of information, dozens of questions and answers can be found there as well. So with that covered, let's talk a bit about what we wanted to do with this study. From what I'd heard from firearms examiners after those first two webinars was really, okay, that sounds great, but now how are we supposed to use it? So what I wanted to accomplish here is really get into how quantum can be used in the crime lab. And so the purpose of the study was to compare how 3D microscopy can be applied to a typical case workflow and establish the differences when compared to traditional comparison microscopy. So essentially, what if quantum was your comparison microscope? And so to do this, I first acquired a number of bullets into a quantum workspace that I gave the name FT Trial Set 1. And the relationship amongst them was that some of these were from known firearms and some of them would represent unknowns. And what I was trying to do is just create this to emulate what could be a case that came to your table there to work, to your desk, and it would represent known firearms from a crime scene as well as exhibits that were recovered from the crime scene itself or maybe the hospital. So within that workspace, I acquired a total of 24 bullets, and they were all from Ruger brand firearms, 9mm Parabellum, 6 right. They also had conventional rifling. They were all cut rifle. And these actually all came, were supplied to us by the Allegheny County Crime Lab. Years ago, they were running out of storage space for their legacy test fires and asked if we'd be interested in having them. We certainly were, and so these were test fires they'd done from casework back in the 1990s, I believe. And actually, to get a bit more specific, with the Ruger brand firearms, the vast majority of these were from P89 pistols. I think a couple might have been P85s, maybe P93s or P94s, but they were all Ruger pistols from that era, with the P89 being the most prominent one. As I was acquiring those in, they were all test fires, all the acquisitions. The 24 acquisitions took me just over 4 hours to complete. And as these were being entered into the quantum system, I was giving them a numerical-based naming sequence. And so there were two acquisitions that were representing test fires from a known firearm. This would have been a gun from the crime scene that you test fired in your own lab. That was test fire 1A, 1B. There's a second firearm that would be test fire 2A and 2B. And then there were a series of unknowns, which I named unknown 01 through unknown 20. With the acquisitions all completed, it was a matter of sorting them out now to be prepared for the comparison microscope portion of the test. And so they were all put in individual bags, and when they were given a randomized letter value rather than the numerical value they had in quantum. So the test fires, there's no reason to change those. That test fire 1A and 1B were still the same, 2A, 2B were also still the same. However, what was unknown 1 through 20 became unknown A through T, and they were in a randomized order as well. So 1 was not A, 20 was not T. The matching sequence, at least, would be different from the comparison microscope experience to the quantum experience. At that point, the data sets were ready to be shared, and so I reached out to Ron Nichols and later Paul Murphy, and the exhibits were first sent to Ron's home in California, where he received the series of bullets as well as a USB external drive that contained the quantum software as well as the quantum workspace FT trial set 1. And the order to do the study was to first complete the work on the comparison microscope, and then with that done, repeat the process using quantum as your microscope in that scenario. Once Ron was finished, the exhibits were then collected and sent to Paul Murphy's home in Virginia, and he repeated the process. So that's the background of the study. So I will pass this over to Ron now, and Ron can explain how his experience went while going through the study itself.
Thank you, Andy, and good morning, everybody. It's good to be with you this morning, and I'm going to be sharing some of my experiences with you. The case circumstances, as I understood them from Andy, were that I would receive 2 sets of test fire bullets from 2 different firearms, and then I would receive 20 fired bullets, all with similar general rifling characteristics. And my assignment, should I choose to accept it, and I did, was to perform a series of comparisons. I wanted to determine which of the 20 fired bullets were fired by submitted firearms represented by the test fired bullets. And for those bullets not identified to the submitted firearms, I wanted to determine which ones were fired by the same firearms, if any. And there on the screen, you can see that I was using a Vision X microscope for this purpose. Now, when I'm working with this many bullets, to ensure the best results, the comparison strategy must be methodical and deliberate. First, I want to compare the test-fired bullet pairs within themselves to check for reproducibility. And then I want to begin comparing the tests with the 20 fired bullets. I would compare TF-01 with unknowns A through T, and then I compare TF-02 with unknowns A through T minus those that I already identified to TF-01. And then I removed the bullets identified to TF-01 and TF-02, and then I built a matrix to make comparisons of the remaining bullets to make sure that I was comparing all the potential combinations. That all 20 unknowns had similar class characteristics greatly complicated this process. And keep in mind also, I want to mention that this is not normally the process that I would use. Typically, I would evaluate all my evidence first and make all the decisions I could make with respect to my evidence. But in this case, I wanted to be able to eliminate as many of the fired bullets as possible against the test fires. So what I did is I did the comparisons against the test fires first. When using the Vision X, approximately 80 hours were spent on the Vision X making all these comparisons. And you can see the results on the right. And the results are shown as numbers to keep the samples blind for future users in case you would like to partake in a more limited set of this. In total, I performed 144 comparisons on the Vision X microscope. Now keep in mind, you can see there's a lot of inconclusive results there. Inconclusive results required extensive comparison because every land engraved area on one bullet had to be compared with every land engraved area on the second bullet. So each inconclusive result required 6 full rotational comparisons to account for every lead-to-lead comparison. 138 comparisons resulted in inconclusive results, so you can imagine the state of my eyes after looking at all these striations and coming up to all those inconclusive results. Now, when I worked with the quantum 3D microscope, my case strategy was different. I used a quantitative analysis to target which comparisons to which my attention should be directed. Now, in this particular case, I could look at all the evidence without being concerned with the test fires because I didn't have to worry about trying to filter out some of those unknowns by comparing with the test, because I could just compare all the unknowns using the quantitative analysis. So what I did is I examined the 20 unknowns by running them against each other with no test fires. And again, this is different than that VisionX approach, because with comparison microscopy, I want to eliminate as many as possible against the test. And then once I ran the quantitative analysis, I sorted by the FMR index. Sorry. And then what I did is I examined the test fires next. First, I looked at TFO1 versus all, and you can see the rebel graph on the right there. And then I examined TFO2 versus all. Now, my overall results were the same as VisionX. The same bullets were identified, and I had the same inconclusive results. So there wasn't any difference in the final conclusions that I reached for the bullets. The same ones that I identified using VisionX, same ones I identified using the quantum 3D microscope, same ones I came up with an inconclusive on VisionX are the same ones I came up with as an inconclusive on the quantum 3D microscope. What was different though were the amount of time that I spent on the quantum 3D microscope. Remember, for the VisionX, I spent about 80 hours. Well, for the quantum 3D microscope, I spent approximately 4 hours of examination and comparison time. There was a tremendous amount of efficiency for comparing the unknowns. I was able to confirm the 12 highest scores, or the comparisons with the 12 highest FMR indexes, in approximately 1 hour as the samples came up in their best match position. I then examined the next 10 highest scores and reached same source conclusions for 3 and inconclusive results for 7 in approximately 2.5 hours. I also examined samples with an FMR index under 2, which is an FMR less than 1/10⁻². But after several, I decided further work would not be of value, because when they came up in the best known match position, there was clearly no correspondence there at all. So it made those inconclusive comparisons a lot more efficient. Once I compared the unknowns, I then compared the tests, and the high scores resulted in a quick confirmation. Now, this is an example of same source with a high FMR index of 19.20. When I pull that up off the rebel graph, because I can click on that and just pull it right on up, you can see the tremendous amount of correspondence. And again, it comes up in the best match position. And when we look at that side by side, you can see the correspondence that is visible there. This is the same source with a low FMR index, and this would be near that separation line that Andy was talking about. Things aren't so obvious here when we look at them side by side, but when we overlap them and merge them together, we can see the correspondence that's existing. Again, this comes up in the best match position, so that when I was able to merge these and overlap these, we can see the correspondence. And then what I do is I just go to the left and I scale down here, and I just move this down, and I'm able to do the rest of the comparison. Now, this is a different source. This is an FMR index of 1.85. And remember, this comes up in the best match position. And as we can see, when it does come up in the best match position, there's not much there. And that's why I was confident when I was doing the inconclusives. If this is the best that this has to offer, there's nothing on here that's going to be looking any better. And again, this is with a FMR index of 1.85, which is in that cloud of data that Andy was sharing below the separation line. So my takeaways from this exercise that I performed: well, many bullets were inconclusive. And again, this makes it challenging, because in order to go inconclusive, I must compare each combination of Lee and groove engraved area on the bullets. And this is much more time consuming than an identification. With so many inconclusive results, comparisons can become tiring on the comparison microscope. And as a result, I can begin to ascribe too much significance to too little correspondence. This is something I've taught for a number of years when I've talked about bias. Quantum 3D microscope helped to rein in some of the inconclusive results that were leaning toward an identification when using the Vision X. Keep in mind, it was still an inconclusive, but what was happening is I was leaning toward an identification when in fact, when I looked at them on a quantum 3D microscope, I was able to rein that in and just bring it back to a straight up inconclusive. Another takeaway is the ease of comparison. When selected from the Rebel graph, again, it presents itself in a best match position. Once acquired, any lighting angle and intensity is achieved with a move of the mouse. The lighting will be the same for both sides. There's no time spent adjusting manual lighting as the mouse movement is continuously changing the lighting until optimum lighting is achieved. And this screen grab on the right shows correspondence with a lighting angle that's not even achievable on my Vision X microscope. And I have a lot of flexibility with lighting on that Vision X microscope. But the optimum lighting that I used on a quantum 3D microscope, I can't even achieve on a Vision X microscope. The other takeaway is that it answers the question for the court, what is that false match rate? Now, they may not be asking that question that way, but courts have been desperate for a random match probability for a long time, and we've been unable to provide that as firearm examiners. Well, the FMR index for each point is calculated, and as we can see, in this case, it is 1 over 10 to the 19th power. That's the FMR index. And the beautiful thing about this, it's caliber independent. So we don't have to have a separate database for 9mm Lugers or 45 autos. This is caliber independent. So we can run that quantitative analysis without worrying about having separate databases. So those are my takeaways, those are my experiences, and now I'd like to turn this over to Paul.
Ron? Okay, good morning, good afternoon, good evening to all the attendees. I know you're from all over the world. Thank you, Ron. Thank you, Andy. I'm just going to share my experiences with this trial. The equipment that I used was an old, about a 30-year-old Leica UFM4 comparison microscope equipped with fluorescent illumination and a Canon 60D DSLR camera mounted on a photo tube. My workflow is as follows. The items that I examined was the same that Andy mentioned and Ron. It's a two pair of test-fired bullets from two firearms with similar class characteristics. 29mm caliber bullets with similar general rifling characteristics. I had to examine and compare the fired bullets microscopically in order to determine which of the 20 bullets were fired by the submitted firearm test fires, and the bullets not identified to determine whether they were fired by the same firearm, if any. The fact that these bullets all had very similar general rifling characteristics made the challenge a lot more, since you could not eliminate anything based on class, so you had to physically compare all the items to each other. My examination methods was as follows. I first intercompared the test-fired pairs of bullets to determine reproducibility. And then I compare the test-fired bullets with the unknown bullets. First, the test-fire pair 1 to the unknowns A through T, and then the test-fire pair 2 with the unknowns A through T, excluding the bullets that was identified to test fired pair 1. Then I did an intercomparison of the unknowns that were eliminated as having been fired in the same firearms as the test fired pairs 1 and 2. I spent approximately 60 hours on the Leica UFM, and I made 228 comparisons and intercomparisons. My results was as follows. I positively identified test fire pair 1 to 2 of the unknowns, and then I positively identified test fire pair 2 to another 2 of the unknowns, and then I identified a pair of 3 unknowns to each other with a 4th bullet inconclusive to that group. My inconclusive results was obviously the one that I just mentioned, is the 1 to the 3 unknowns. And then I had one group of 3 unknowns that was inconclusive to each other, a negative to the test fire pairs, and the remaining 17 unknowns. And I had another group of 2 unknowns that was inconclusive to each other, a negative to the test fire pairs, remaining 18 unknowns. This is just some comparison microscope images of the first one is test fire 1B to bullet G, test fire 2B to bullet E, and bullet C to bullet D. That was part of the 3 unknowns. That's 2 of the 3 unknown groups that I identified to each other. My strategy with the quantum 3D microscope was fairly similar to the conventional comparison microscope. So I first intercompared the test fire pair bullets to determine reproducibility. I then intercompare the 2 test fire groups by means of quantitative analysis to determine which bullets would be examined visually with a comparison viewer. So it was test fire pair 1 to 20 unknowns and test fire pair 2 to 20 unknowns. Then I intercompared the 16 remaining unknowns by means of quantitative analysis to determine which should be examined visually with a comparison viewer to determine a common source. And this is the unknowns to each other. Here you can just see the RBL graphs of the two pairs of test fires, and that was the intercomparison to determine the reproducibility of the test fired pairs of bullets. This is another examination method of the test fire 1, A and B, to unknowns 3 and 9, and a combination of the RBL graph as well as the visual comparison viewer. These are test fire 2, A and B, that was made positive to unknowns 6 and 14. You can see here is the images from the comparison viewer, and this is the RBL graph. Then I used the quantitative analysis to determine which of the 16 remaining unknown bullets should be intercompared. I was able to positively identify unknowns 5 and 20 as having been fired from the same source. And then I was able to positively identify unknowns 4, 13, 17 as having been fired from a same firearm. And then groups, unknown group 7, 11, 15, and 19, which I made then positive to each other, having been fired in the same firearm. Now, the first two groups here was the ones that I called inconclusive on a conventional comparison microscope. And the bottom one, there was one bullet that was inconclusive to the group. And the combination of the RBL graph as well as the superior images from the comparison viewer enabled me to make a different result going from inconclusive to positive. I spent approximately 2 hours on the quantum 3D microscope to examine the 24 bullets. Test fire pairs were examined and compared, resulting in matches of 4 unknowns to the test fires. The unknowns were examined and compared, resulting in 3 groups of unknowns as being fired from a common source. The positive conclusions for the 2 groups of unknowns I determined as inconclusive on a conventional microscope. And also the positive conclusion of the 4th bullet that was made inconclusive on a conventional microscope. I saved over 50 hours, which is a huge saving with quantum 3D microscope analysis and the 3D comparison view. To my opinion, the quantum 3D microscope is a lot faster, it's much more accurate, and it's very user-friendly.
Thank you, Paul. Great. Okay, so now we will move forward, and I have a series of questions actually for both Ron and Paul. First, we can just take a quick look at the summary page here. 80 hours of microscope time for Ron, 4 hours on quantum, 60 hours for Paul, 2 hours on quantum. You could actually add my acquisition time to this. This was their comparison time only. There was also the 4.5 hours of time that I spent doing the data entry. So that brings Ron total time would be just under 9 hours and Paul just under 7 hours. So let's go with a question here for Ron. There was a major difference in the amount of time to the comparisons between your conventional comparison microscope and quantum 3D. Where do you see the 3D imaging having the biggest impact to give you that amount of time saving?
Well, the primary is just the fact that once they're in the system, I can just pull them up and adjust the lighting however I want to adjust it. I have really good stages and mounting systems for the Vision X as well as lighting, but it still takes a tremendous amount of time to adjust that lighting, make sure everything's equal on both sides, swapping out between the bar light as well as the ring light and the spotlight if need be. So there's a lot of things that are going on, and when we're dealing with as many inconclusives as we're dealing with, I'm going to be looking at different lighting options to try and highlight those striations. But when I was looking at the quantum 3D microscope, it was just so much easier because, again, I could adjust that lighting within seconds, and I could be assured that it would be the same on both sides. I could adjust the coloring if I wanted to, the depth. And so the comparison was just a lot easier. Also, I didn't have to search for my, the best match position on the quantum 3D microscope as I would. I mean, it still takes me time to phase my bullets. There's a 1 in 6 chance I'll end up in a phase position if I have 2 matching bullets. And if I don't, well, then I'm going to have to search around for that. With the quantum 3D microscope, it was just so much easier to use a quantitative analysis to target those comparisons. So it just made it a lot more efficient.
All right. And Paul, there were no instructions actually for Ron and Paul. We didn't give you instructions on how you should approach using quantum. We wanted you to just sort of see what came naturally to your mindset. So Paul, when did you apply the quantitative analysis application to the workflow while you were using quantum?
Well,
Paul?
Okay, sorry, I was just unmuted for a while. I applied the quantitative analysis right in the beginning. I first look at the quantitative analysis, and then based on that, I looked at the high score values, and then I called up the images on a comparison viewer.
Okay. All right, and that felt that felt like a natural workflow for you as far as just your approach. It was intuitive to go that route, I suppose.
Yes, that was, as I say, I did not obviously have the luxury of a quantitative analysis as well as superior images on a conventional microscope. It is a very old microscope that I was using with very limited illumination. So the images were already in the comparison viewer, and I could just pull them up and look at them and do the comparison side by side.
Okay. So Ron, how do you envision 3D microscopy entering the firearms lab?
I see it entering in side by side with comparison microscopes. I mean, there's still going to have to be internal validation with respect to examiners. We've built our entire data set on using a conventional comparison microscope. You know, we look and make determinations on whether or not two bullets share a common source by evaluating what we're observing against our best known non-match, and is this consistent with what we expect to see in known matching conditions. Everything has been developed using conventional comparison microscopy. Well, when we're looking at the quantum 3D microscope, we have a lot more information with which we have to deal. And so it's going to take some time to get used to the amount of information we're seeing using the quantum 3D microscope versus conventional comparison microscopy. So I see them existing side by side. And at the same time, as examiners get more and more comfortable, as the quantum 3D microscope becomes validated internally within laboratories, I see a transition going to the quantum 3D microscope. It won't take it over because there's always going to be a use for conventional comparison microscopy, but I do see the quantum 3D microscope and virtual comparison microscopy really being the go-to for examiners in a forensic laboratory.
Okay. And Paul, where do you see the biggest hurdles in adapting 3D microscopy?
I would say we have to convince the courts. The community will have to meet up with prosecutors, judges. We have to introduce the technology to them and then show them the value of the technology. And once the court accepts this, I think we'll be good to go with this.
All right. And Ron, do you have concerns about calling a match on a pairing that has a low FMR index, something that's below that separation line, rather than something that's comfortably above it, let's say?
Anything that's comfortably above it will be much easier. Things that maybe have a low FMR index or maybe below that separation line, if there's sufficient correspondence in an area that really does indicate that these two items share a common source, I wouldn't hesitate at all. Because keep in mind, as you mentioned, Andy, that FMR index can be low if a good portion of the land engraved areas are relatively smooth. And we can encounter that in casework. And at the same time, there can be areas at the base, small areas, maybe a portion of the land engraved area at the base that has really strong striations. So if that's the case, and if those exist and they correspond well, and it exceeds the best known non-match, and it's consistent with what I would expect to see in known matching conditions, I wouldn't hesitate at all. I just have a little bit more explaining to do in court, but I'm not afraid of that.
All right. And Paul, do you have concerns that the quantitative analysis pointing you to an alignment between two bullets and also even the FMR index do you think that that could be introducing bias into your comparisons?
No, not at all, because a lot of time it's like when I look at the inconclusives on a comparison microscope, and after I've looked at the quantitative value and I looked at the images, and I was able to see the images in 3D, I actually went back to the comparison microscope to look at some of my inconclusives, and since I know that they were matching pairs, I was changing lights and angles, and I could see more than I've seen before.
Okay, all right. And I guess this is a question for both of you, although Ron's touched on it already, but do you see 3D microscopy replacing the conventional comparison microscope?
I don't, because right now there's the issue of tool marks, and there's a lot of things that won't fit into the quantum 3D microscope to be imaged, and will receive casts from crime scenes, whether they be burglaries of FFLs or scrape marks from a safe or what have you. So there's a lot of items that a firearm and tool mark examiner will be examining and comparing that still will require conventional comparison microscopy.
All right, Paul, do you have any thoughts yourself?
Yeah, well, I agree with Ron. I would say the 3D microscope will complement conventional microscopy, but it will never replace it, or due to logistical things such as the size of items. Sometimes you want to look at a serial number on a slide of a firearm, and you put it on a comparison microscope. You will not be able to do that, or you have some cut marks from a tool mark case that is pretty big, or a piece of lock, and those are items that you cannot do it with a quantum 3D microscope. So you will have to use a conventional comparison microscope. So I don't really see it at all replacing them, complementing definitely. Okay. And also the quantitative analysis, the court has been asking for this for a long time, and I think with the quantitative analysis that we have in the quantum 3D microscope, together with a comparison viewer, that's just going to be another tool for the firearms examiner.
Hey, Andy, this is Michel. I have a question here from Jordan Green, if you don't mind. He asks, sure. Would we expect that the quantum 3D microscope would reduce the number of inconclusive results? I'm not sure. I think that you covered this in your panel discussion, but still, it's a good question. If it would reduce the number of inconclusive results overall. I think we saw that in Paul's experience. Any comments?
Well, I can just
go ahead, Paul.
Go ahead, Andy.
Sorry. Well, yeah, I think that we saw that with the test here. I think there were inconclusives with the scope portion of the trial, of the study rather, that had a much more conclusive result using the quantum software. Paul, I think that was mostly on your side. Do you find that that's the case, that the use of quantum would be leading to less inconclusives, I guess, between your comparisons?
Yeah, I would certainly think so. As I say, with this trial that I've done, I definitely, my inconclusives when I was looking at them in 3D and already having a index to start to look at, it definitely helped me change the result. I actually did in the past, even before we had the quantum 3D microscope, I did a test with Glock style bullets on a conventional microscope, and then on Bullet Track's 3D images. And again, knowing that there are matching areas and knowing where they are, going back to the conventional microscope, changing the angles and the lights and magnification, so here and there, definitely was a great help.
And I think for some of those more difficult ones, just the fatigue that you get into, like working with polygonals or on some of these ones that were so similar, when they are that similar, the fatigue that you go through mentally must be a factor as well with what you go through. Sorry, Ron, I cut you off there.
No, it's okay, Andy, and that's true. The fatigue is an issue. There's a lot more data to work with, so I do believe that there could be, as Paul experienced using his Leica, that there could be less inconclusives when using a quantum 3D microscope. At the same time, my experience is I'm going to have a lot more confidence in my inconclusives, and I'm going to have a lot more confidence in those inconclusives a lot sooner than I would have using conventional comparison microscopy. Inconclusive results take a long time to deal with, and it is exhausting at times. And so we have to be careful about the amount of time we're spending on a microscope, because again, we can begin to ascribe too much confidence in too little correspondence. So not only does a quantum 3D microscope provide us with more data to reduce the inconclusives, when we do have those inconclusives, it gives us greater confidence in them.
Well said. Is there anything else, Michelle?
Yeah, there's another question. Well, actually, a couple people asked a similar question, which we've covered in the last year's webinar, about the fact that this quantum 3D microscope experience is applied to bullets. Patrick Kurtzman asked this question, is if we're looking at moving into cartridge cases as well. And yes, this first model of quantum 3D microscope is well suited for bullets, not as much for the large flat areas on cartridge case heads, although we can use this current model for the chamber marks and ejection port marks and other marks on the sidewall of the cartridge case. But we are working on similar solution for the regions on the cartridge case head. And we'll let you know for sure when we're ready to show you something. So that was me answering, not you guys. And other question here, Ron, probably for you, because you mentioned internal validation. It's a question from Stephanie Luer. Regarding internal validation of 3D microscopy within casework, would this include a user acquiring the images or the examiner performing conclusions with the quantum 3D microscope, or both?
The answer is yes. It would be both. We have to deal with the acquisition as well, so that has to undergo a validation as well. And at the same time, the quantum 3D microscope is calibrated, and so it measures that. And then, of course, we have the issue of, am I going to have comparable results when I'm doing conventional comparison microscopy versus the quantum 3D microscope? And the FBI introduced a similar internal validation approach when they were looking at virtual comparison microscopy by pulling up old casework and acquiring those images and masking what that casework was. And then the same examiner would go through and perform comparisons. And what they would do is they would compare the results of what they got on a conventional comparison microscope versus what they got on virtual comparison microscopy. So something similar to that can be done. There's many different ways to conquer that beast, and it just has to be thoughtful, and it has to demonstrate that the quantum 3D microscope is fit for purpose in that laboratory.
Thank you, Ron. I have a question here from Thomas Sismore. I think it's akin to the question about the quantum 3D microscope replacing the conventional microscope, but it's asked differently it's more about the quantum 3D microscope. Is it likely to replace the match point, like the IBIS match point at all? This is a confusing question, Thomas. IBIS serves a completely different purpose than the quantum 3D microscope. to answer your question, 3D microscope is for microscopy and IBIS is for search. So the IBIS will continue searching for previously unknown links between crimes involving firearms. And whatever is found, like a Google search from the IBIS system, will be brought into a microscope, either conventional or 3D microscopy as we go into the future. So no, although you see similarities in the side-by-side viewing capabilities of Matchpoint and the quantum 3D microscope, there is no intention of the two different purposes, the two different products of converging. I hope that answers your question.
If I could just expand on that for a second there. Tom, a good way to think of it is that your IBIS system within NABIS is still going to be searching your location as well as all across the UK for possible matches. But once you've found a potential match using IBIS, Quantum could be the tool to use to confirm that match or be your comparison tool for the confirmation side of it. IBIS is the search, and then Quantum is the tool for once the potential has been found. Now, what do you see? It's different. There's different algorithms taking place between an IBIS search and the quantitative analysis program that's running within.
Yeah, and Daniel Roberge actually had a section on that in the first webinar. I think he did cover that well, the differences of the system. So Thomas, if you have a further question in that line, you can email us. And on that note, there are no other questions pending in the queue, and we're coming up to the hour. So anyways, if you have any more questions, don't hesitate to contact us. But what I'd like to do now is thank our presenters, Andy, Ron, and Paul, for this very informative discussion. And hopefully we addressed some of the questions that were not asked, but people had on their mind. Note that we'll be publishing a report in the coming weeks detailing the contents of this study. And so, like I said, you can contact us, visit our webpage. Some answers might be there in the previous recordings, of the previous webinars. And you can always contact us. We're happy to talk with you. If you'd like to participate in a similar study, you can contact us again from that Quantum 3D Microscope webpage we have on our website. You can use the request information link. And this should involve a smaller subset of bullets to reduce the amount of time required. Because I believe if it's between 60 and 80 hours on the comparison microscope and a few more hours on the quantum 3D microscope software, I'm not sure we'll have that many volunteers because it is quite a bit of time to do a massive subset. But anyways, please contact us if you're interested, and we'll be supplying double-casted bullets to perform that subset of the study. So this does conclude the webinar. On behalf of Forensic Technology at Ultra, I'd like to thank the presenters for their work and for sharing their experiences, and we appreciate everyone who took the time to attend today. So goodbye, and stay safe and be well.